So here we are on the 24th of February. It's class number 9, packet 5. Today we'll talk about Mars and the Mars probe we've sent up there, Perseverance, and we'll talk about, we'll do a little bit on the 5 graphs. Okay. So like I said in class, we spent a lot of time going around giving dinosaurs to students who have been keeping up with their homework. Here it's due, 5.2 is due Thursday at midnight for you. That's you guys right there. That's for you. 5.2 Thursday night now. You can turn it tonight if you want, but Thursday night, I'll give you extended in a day because of the mix up on the how to submit. To me, my fault. Okay, so I'm going to try and share a different screen. Let's see if this works. And I bet YouTube's going to freak, because they get all these copyright issues whenever you try and share a different screen. Oh, where'd it go? Where'd it go? Where'd it go? Let me find it here. Easy draw, easy draw, easy draw. Mail, Google Chrome, that'll work. I'll share that one. Okay. And it's not the one I want, but okay, hold on. Yeah, that is the one I want. All right, so we'll start with this one. And I'm hoping you guys can see it. Can you guys still see the screen? It says, you see what it says there?
Yeah, you're good.
It says Dare Mighty Things. Okay. You may have seen this one, I don't know, but this is one of the better ones I've seen. So as we go through, I'll pause it and talk about some things, okay? So I don't know, take notes, don't take notes, sit back, relax, but maybe just not take notes, just think about it. Kick back.
When people look at it, it looks crazy.
Sound okay? And let me know if it's like, what? Turn it up? Okay, let me change. Yeah. Hold on a minute. Let me just change. I'll turn that off. I have an external speaker. Okay, now I have internal speakers. And let me know if it's too laggy.
That's a very natural thing.
As loud as it gets.
Sometimes when we look at it, it looks crazy.
So 76 Pyrotechnic Devices. So things, you're carrying along that much to Mars with you, things that explode.
It is the result of reasoned engineering.
Okay, so 500,000 lines of code. For a typical bot in BotBall, depends on how difficult the course is that we're working on, but it's 300, 400 lines of code, maybe up to 1,000 lines of code. We had one bot that we had 6,000 lines of code, and it did nothing. It just sat in the starting box. There was so much code that it couldn't even. Kept looking at its situation. So those are autonomous bots. This is an autonomous bot. When we first started going to Mars back in the 90s, Dr. Miller, who's now started robotics, started BotBall, but he was on that first mission with JPL, and the engineers were wanting to make it remote control, make the bots remote control on Mars. Well, that's a little bit of a problem. You can do it on the moon, because the moon there's only there's about a 2.6 second delay round trip. But on Mars, it's 20 minutes round trip. So, 10 minutes one way, depending where Mars and Earth are. It just takes a long time, even at speed of light, to get the signal there. So if you're running into a rock, you cannot turn left. By the time you turn left, you've already hit the rock. So they have to make them autonomous. And that's why he started BotBall program, was to get students to start to code early in their life, and Code Academy, that kind of thing. So right now, there's something called Junior BotBall, and we have students that are in kindergarten that are coding. So you might want to learn some code. I'm old enough, we're all kind of, I know Fortran. I learned Fortran in college. And so I know Fortran fairly well. I did. Used to use it all the time. But now it's like Python and things like that. So this COD 3, I'm not sure what that means. What is it, code, or I don't know what that means, but 500,000 lines. I know a line of code, what it does. So it gives a command, right? And you have all these commands. So this is the most sophisticated robot we've ever had, and we're sending it up there to. It has to. Since we can't control it, it has to react to its environment in real time.
Thought, but it still looks crazy. The top of the atmosphere, down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive and dead on the surface for at least 7 minutes.
Entry descent warning, also known as EDL, is referred to as a 7 minutes of terror because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
So you get that 1,600 degrees, which is really amazing to me because there's only 1% the atmosphere on Mars than it is on Earth. Now we return back to Earth, and the space shuttle stuff has to have those heat tiles, right? I mean, Columbia had a few of them missing, and it blew up over Texas. So it just gets really hot, and it makes sense on Earth because our atmosphere is so thick. But even at 1%, less than 1%, and we'll talk about that here in a second, but it still generates all that heat because it's mostly carbon dioxide on the surface of Mars, but the carbon dioxide molecules cannot get out of the way fast enough. And so they just keep building up, and all this friction creates all this heat, 1,600 degrees. So we need this strong heat shield, even on Mars. We don't need it on the moon. The moon really doesn't have any atmosphere, but Mars we do.
Entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand,
okay, so let's pause for a second. We paused in class on this and talked about it. So Mars atmosphere, it's about 95% carbon dioxide. On the Earth, anybody know what the percentage is of carbon dioxide on Earth's atmosphere? You can chat it if you want. It's less, it's about 0.4%, somewhere in there, 0.04%, because there's not a lot of source. You know the main source for carbon dioxide on Earth? Where does it come from? Main source is us, right? At least in a room, if we're in a room. So, because we breathe out carbon dioxide as waste. So of course it's as all we have is carbon dioxide, we're going to suffocate. So it's about 95% carbon dioxide. That's a huge difference. It's about 3% nitrogen. And if you're in chemistry, you probably know that nitrogen on the Earth dominates. It's about 80%, 79%. But the Earth's atmosphere is about 80% nitrogen. So I wrote on the board a bunch here, but I really don't want to pause this. I don't want to switch screens. So anybody, I bet you Miranda knows this one, and the chemistry people know this one. But why, if nitrogen is 80% of what we breathe in, why don't we react with it? Why don't we use that nitrogen in our body to do stuff with? You think we'd be nitrogen would be the thing we would have evolved to use. Why not? If it's 80% of the air we breathe, if you take a deep breath right now, 80% of the molecules you breathed in is nitrogen.
Maybe because nitrogen takes more energy to breathe in.
Nitrogen takes more energy to break up. So it's triple bonded. So there is nitrogen, but there's a triple bond between the two. It's a diatomic. And if you've taken chemistry, you learn about the 7 diatomics, you know, the O2, the Cl2, the N2, the 7 diatomics. Well, nitrogen is double bonded. So there's triple beams, there's triple cables between them. And it's like 900 and some odd, it's been a while since I've taught chemistry, joules per mole or something like that. To break it up, it's really difficult. So our body can't break it up. So we breathe in the nitrogen into our lungs, and we breathe it right back out. But that's not really important, I guess. What's important is oxygen. Our air is 20%, about approximately 20% oxygen. But look at Mars, only 0.13% oxygen. So that's a bit of a problem if you want to breathe. And then you have argon. What the heck? Argon is like it's a noble gas on the periodic table. And we have argon on Earth too. About 1% of our atmosphere is argon on Earth. Where does argon come from? It's a noble gas. That seems odd. Why argon? Anybody want to throw that out there? Anybody heard this one before? Why
Isn't argon?
say again?
I was gonna say, isn't argon like the byproduct of oxygen and nitrogen?
No, it is a byproduct, but it's a product of radioactivity. The potassium and stuff in rocks, just rocks, they naturally decay, and that one of the products of that natural decay, and the half-life is huge, millions of years, I believe. One of the products of those is argon. So argon's by the Earth is producing argon. It's radioactivity essentially, but argon's harmless. It's a noble gas. Its nucleus is stable, and so but if you breathe in, you're breathing in thousands of atoms of argon, but you breathe it out again. It doesn't really react with anything. So there's argon on the Mars for the same reason. It's a third ingredient. Same on Earth. Argon's the third ingredient. That always blew me away. I never understood that until I learned a little nuclear physics. So there's not much oxygen. There's carbon monoxide. That's enough to set off a detector, I guess. That's bad on the surface. We don't want to be breathing that. And there's even some water vapor. But the thing is, once you look at on Mars, the surface pressure is 0.004 pounds per square inch. Now, anybody want to venture a guess or look it up or remember what is the PSI for Earth? How many pounds per square inch of force is pushing on you right now?
14.7.
There you go, Io. So there's the two zoom points. That is 14.7 PSI, 14.7 pounds per square inch. If you multiply that out, it's about 2,000 pounds per square foot on your body. All this force is pushing in on us from the atmosphere. Our body pushes out with the same amount of force. That's why when you cut somebody open or cut open a calf or whatever, I mean, it just all the guts come flying out like they're on springs because there's a lot of pressure inside the body too. So anyway, the atmospheric pressure on Mars is only 0.004 versus 14.7. So you can tell that there just isn't any pressure up there, and that's going to be an issue. That also affects sound waves. They have a microphone on Perseverance, but if you got to really listen close to pick up anything, they say it picks a little Mars wind up, but people want to hear Mars. You're just not going to hear much unless you really amp it up. Okay, let's keep going.
And it doesn't have enough atmosphere to finish the job. Still going about 1,000 miles an hour. So at that point, we use a parachute. The
parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand
Okay, that's Anita Sengupta, and she was sort of a rock star here for this landing. I believe it was her that you kept seeing when she was kind of the narrator of what's going on, letting everybody know where we're at, what's the altitude is, what's the speed is. Now the first person that NASA wants to step foot on Mars, they want it to be a woman. And I thought to myself, well, maybe it would be Anita, but I'm thinking she'll probably be too old by then. By the time we send a human to Mars, or a human team to Mars, my guess is somebody could look this up real quick. Maybe you guys already know. I don't know it keeps changing. The proposed date of when we send humans to Mars. 2040 would be the earliest. So Anita is probably 25 there, 30, maybe she'll be 50 years old. So it won't be her. It could be one of you, or it could be somebody that's in first grade right now. So we don't know for sure, but definitely NASA said it'll be a woman. And they've even talked about having an entire woman team where it's all women that goes to Mars. So I think that'd be pretty awesome. Anyway, so she right now is a big rock star in NASA.
65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck snapping 9Gs.
Now, 9Gs, we watched those, remember to watch those fighter pilots, and they put them through those Gs and they'd pull that lever back. And the faster they pull the lever back, the quicker they'd pass out. So that went from 1G all the way up to, like, I think I saw 9Gs. Well, by usually about 7Gs, depending how fast they pull it, they're passed out. Now you're going to go and you're going to stroke. I think you'll stroke out at 10. I mean, if you do it quickly. So you can't put humans in this kind of a situation. So we'll have to do it a different way. We can't do it with this parachute. But the first time we landed on Mars, it was a bunch of balloons that popped up, that came up, and then the whole thing bounced a bunch of times. And then the tiny little rover, that little Pathfinder, came out. But anyway, so we're getting more and more sophisticated.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert. Fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside 6 kilometer high mountain.
So they're going to land. They landed in a lake bed, they think, and so an ancient lake bed. So they're going to, one of the first things Perseverance does is going to drill down and core sample. I don't know how it doesn't go that deep. They're going to core sample. Then they're going to take those samples and set them aside. And what Dane Sholin from Norman High, there was an article of him, by the way, in the transcript this morning. But what Dane Sholin is doing, his team, is they're working on when we go recover that in 2031. So he's now got a 10-year project set up in front of him to figure out how to get up there, not just land on Mars, but then be able to take off from the surface of Mars and come back to Earth. That's never been done. Now that's kind of stuff we got to do before we can send humans, you know.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms, and it could damage instruments. So the way we solve that problem is by using the sky crane.
20 meters above the surface, we have to lower the rover below us on a tether. It's 21 feet long, and then gently deposit it. on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. You must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
Now I don't know. I'm guessing that thing just goes off and crash lands. So we're building up this junk. We're starting to trash out the surface of Mars with all these different instruments, and it's not like on the moon. Neil Armstrong's footprint is still there on the moon, and pretty much the same situation it was because there's no weather, there's no wind. But on Mars, they get some substantial storms. Even at 1% the atmosphere, they get some big, huge, 1,000-mile wide storms. So it could get buried in sediment by the time we finally get there to retrieve it. But anyway, so we're building up all this little junk everywhere. Okay, so then the other one I wanted to show, this one's from Dr. Rambo, Carl Rambo, a friend of mine from OU. And this is really good because this is actual
and fly right maneuver.
This is actually real footage that they've acquired since, because remember, it's got to send out that footage, and I don't know how many megabits per second it can send out this video, but it send the video back to Earth, and then now we've processed it. Now this is the real video of the lander. Here we go.
Where the spacecraft will jettison the entry balance masses in
Anita
preparation for
talking
parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and
Now remember, we're not watching this when it's happening, but they're getting the sensors. And by the time they're getting the data, the rover would have already crash landed if it hadn't. We wouldn't have known it.
Seeing significant deceleration in the velocity. Our current velocity is 480 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
So now those are real cameras there. Watch the heat shield go away. Now you're not looking at an animation. Real cameras at the surface of Mars. It's got that red look because of all the iron oxides, a lot of rust. A lot of iron oxide on Mars.
To subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
So it's got the parachute on it, still descending very quickly. You just can't catch enough air. Remember, the formula for air drag is 1/2 d rho AV squared. Well, the A in that is the profile area of the parachute, or whatever it is that's falling. And then but the rho is the density of the medium it's falling through. So on Earth, the density is 1.2 kilogram per cubic meter. But on Mars, it's like 1,000 times less than that. So 1,000, somewhere in there. Maybe it's not quite 1,000, but it's a lot less than that. So it just does. You don't have the air drag you need to go really slow. Still going like 200 miles an hour.
Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers of the surface.
No, it's computers now are taking over.
Continuing to descend on the parachute.
We're not controlling it, so it's looking down those 500,000 lines of code, is looking down to try and find the best place to land. In Apollo 11, Neil Armstrong took over manually because the place that they had set the Eagle to land was, they found out, it looked just him and Buzz Aldrin just looking through the windows there. They said, wait a minute, there's way too many rocks here. And so Neil Armstrong had to take over and manually land that thing. It's like flying a wash machine. It's not aerodynamic at all, and there's no air anyway. But he if you've ever seen the movie, it's pretty amazing. He finally pinpointed that landing in a better place. But they don't have Neil Armstrong here, so they have to. So the computer has to do it on its own.
Shoot, we're coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
So now it's starting to sound like a physics problem, right? Free fall. And we could do, you could use the blue free fall equation. You change the G to, I think it's 2.67. I think that's what Mars is, somewhere in there. But then you got to add in all these other features, not really wind, but you got to add in that bit of air drag that they have. And G is actually changing as you get closer and closer to the surface. It's going up.
Oh, yes, valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. PBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is
All
about
right,
7.
so now they have cut off that the parachute, and now it has doing that sideways maneuver, because if those engines fire, it'll fly back up into the parachute. So it goes to the left or the right a little bit, then it sets its engines off to fire.
75 meters per second at an altitude of about a kilometer off the surface of Mars.
Here in safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity.
Okay, now you see those engines are kicking up that dust. Look how fine that dust is, very fine powder. And that's gonna come up, and then if they don't jettison that and get that thing out of there and cut the cables, because they're gonna lower in just a minute, they're gonna lower the rover onto the surface, but then it's gotta get out of there, because otherwise it'll just put dust, it'll cover all the solar panels, it'll get into all the instruments. So they're about to go to 3 screens here.
Accordion, which means we are conducting the sky crane.
Now, the screen here on the upper left, that's looking up, and there's a cable there. And then the screen below, that's the lower, that is the rover itself. Okay.
About to conduct the side crane maneuver.
There it goes. So now you're looking up on this, on the upper left, you're looking up, and on the lower left, you're looking down.
Sky crane maneuver has started.
Actual footage.
About 20 meters off the surface.
Kind of looks like Mars. Looks like it has blue skies up there, doesn't it? The sky really isn't blue on Mars. It doesn't have the same molecules in its atmosphere. But maybe it's a cloud formation up there. So they do have clouds. Maybe it's just
We're getting
dust.
signals from MRO. Tango Delta.
Touchdown
Okay, it's
confirmed.
gone.
Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
And so these people are cheering like crazy. I asked Dane where he was. He was in the next room because of COVID. They had to only have 50% of the people in there. But these people are cheering wildly because it's about 5 to 10 years of their life. If this thing had crash landed, heads would have rolled, and they would have, some people would not have had much of a job to do, because now they got their experiments to do. I mean, they're working on other projects as well. Like Dane's working on Mars. He's the driver for Curiosity, and also he's working on these robots to go down into tunnels on the moon. So they have different projects they're working on, but you want these things to work. Okay, so that's kind of cool. So there we go. We talked a lot about that in class, and I guess we're about where we need to be to go to the next thing. Anybody have comments or questions about it? Did anybody find out when the next planned manned mission is to Mars? look that up before we go, and then you chat that up or say it. I'm kind of curious. I'm going to guess 2040. And Elon Musk always extremely, he's always this. I'm talking NASA, but Elon Musk is always extremely optimistic. I think he's saying 2030, but I don't think so. We'll see. But my guess is, in reality, it'll be 2040 at the earliest. So, how old will you be in 2040? 37, 38, 36. You'd be at the right age to be one of the leading candidates to go. You got to be a woman. So, maybe Rose can be the first one to step on Mars, or Sophia or something. But there'll probably be men, but I mean, in the team, I'm guessing. I doubt they'll have an all-woman team. It'd be cool, but I doubt they would. Anyway, so hopefully it'll be an American, I guess. Doesn't matter. Earthling. Okay, so let's do one more thing. And that is, we started this. Let's go ahead and finish it. We were looking at the last couple of minutes on number 2 on 5.3. So the homework, this is not homework. We'll do 2 and we'll do 2 and 4 together. This number 1 is homework, and that's going to be Monday. And number 3 is homework on Monday. Okay. So let's knock off number 2, and then Monday we'll knock off number 4. Remember, tomorrow we don't meet, and we don't meet on Thursday either, because they'll be taking the test tomorrow, and so we don't meet on Thursday or Friday. Okay. So blow this up. I shouldn't have done that. So we have the general shape. We did that yesterday. Figured out what the general shape will be. But now we need exact numbers. So to go through and do this, see if I can knock it out in 13 minutes. All right. Let's start. Let's always start with the red. Let's go as far as we can in the red. Get that low-hanging fruit here. So we have delta x. Delta x equals v naught cosine theta times t. And we know theta, we know time. So delta x equals v naught cosine 40 degrees times 4.5 seconds. So we know all that, but we have 2 unknowns. I don't know v naught and I don't know delta x. So over here on my right triangle. Okay. So let's see. That's as far as I can go. I can't really do anything there. So I have to go to the y, and you go to that second y. And I'm going to do this different than class. Second arrow, we kind of screwed up. Okay, how about we go, more careful this time. Let's go delta y equals v naught y. V naught y is what I want. So I'm just going to say v naught y, which is v naught sine theta. But v naught y t minus 1/2 gt squared. So let's see if I can do this one. No. I have t. Good. Boom. Oh, good. It's type 2a. So it's 2a, so I know that delta y is 0. Okay, so we have, and then one of my t's goes away because of that. We've done all this. This is old news. And so t then equals 2 v naught y over g. Total, that's tau. Let's see if I did that right. Tau. Did I do that right? Oh, no. I'm screwing up here. Sorry. Wait, that's right. Yeah, 2 V naught Y over G. That's right. Okay, but I want to know V naught Y. So V naught Y, sorry, I solved for the wrong thing, is tau times G over 2. Okay. Yeah. So I have 4.5. I'm trying to do this smarter than second hour today. 4.5 seconds times 32.2. The feet, it's in feet here. So 32.2 feet per second squared divided. Oh, gosh. This is what happens when I get in a hurry. Times G. Oh, that's right. Sorry. 32.2 and then divided by 2. Okay. That's what I need to find. And I think when I do that, I'm going to get V naught Y. Someone can tell me if I'm wrong, but I think it's around 75 feet per second. Is that what you're getting?
I got 72.45.
All right. Anybody else agree with that? 72. That seems too small. I thought it was 75 we got. But
I
maybe
got that too.
you got 72?
Yeah.
Fair enough. Okay, I believe you. 72 feet per second is my V naught Y. So now I go over here and I go, okay, I'm starting at 72. Well, I had guessed yesterday when we were doing this in a hurry, I guessed about the right guess. I might have got lucky and got credit for that one. Because I got it right there at 20, 40, 60, almost at 72. That could pass for 72. So my initial point is maybe a little bit too low. Initial point's right here at 72. Now I almost got the whole thing done because now all I got to do is let me erase that to get that a little closer to correct. Okay. So now all I got to do is I start at 72 and I know I'm going to be at 0 at 2 point, and that's someone pointed out yesterday. I am off a little bit. Shoot. Sorry, this is for the record here. I got to have this kind of right. Okay. This is off a little bit. It's 2.25. 2.25. So because 4.5 is where I end up. So 2.25. So that dashed line, that's my apex, and that's where I'll end up crossing 0. So this then starts off at 72, right there, and it's gonna be at 0 because it's 0 velocity at the apex. So I can just link those two up. By the way, that would have a slope of 32.2. And I end up like that. So that's a perfect bow tie because it is type 2A. See, we keep coming back to the same themes over and over again. Eventually you go, okay, now I get it. That's the idea anyway. So this is my positive area. Now, if we shoot it from the surface of Mars, the slope would be just a lot less, but it would still look the same. It'd still be a bow tie, even better bow tie, because there's just not air drag really on Mars, hardly, unless you're going at supersonic speeds. Whenever they say supersonic, that means speed of sound. And so speed of sound is around 330 meters a second, or about 740 miles an hour. So when they say supersonic, that means that thing is going around 800, 900 miles an hour when it comes into Mars atmosphere. So now I got to find, I know I start here at 0 because that's a football being punted. I end at 0, and I know somewhere in the middle I'm at my apex. So I just got to figure out what that apex is. 2 ways to find that. One is third blue. How much time have I got? 6 minutes. Okay, third blue. But now we know V apex is 0. So we say 0 equals V naught Y squared minus 2G delta Y. And so the delta Y then at that point will be V naught Y squared divided by 2G. All right, so you can punch in your numbers. Or another way of doing it is just realize it's the area of this. And I like this is more the calculus way. So the area of this red right triangle, 1/2 base times height. Well, the base is 72. The base is 2.25. I'll do it this way. I like this better. It's quicker. So we have 2.25 for the base, 2.25 seconds times a height of 72 feet per second times 0.5, 1/2 base times height. I get 81. So this football will go 81 feet in the air. That's right up here at the top then. 81 feet in the air. And so it comes up kind of like the St. Louis Arch. It's not really a parabola, but okay. And there you go. And now what we got to do is do the X real quick before we got to go. And the X, we know what the shape, oh no, okay, we know what the shape is. We know it's flat and then linear, but the question is what? So let's find that, let's find the blah, 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 blah. Oh, all right. Oh, huh. We got to find VX. We never really found VX. Oh, okay, we can find it this way. We know that yeah. I haven't tried it this way. Let's try it this way though. We know that VX is 72. So back to this right triangle, I'm trying to find different methods of doing this. So back to this right triangle. Let's erase that, get that mess out of there. I want to know if I know that's that side 72 and I know that the angle's 40. This is why you learn calculus. Then I know that the tangent of 40 degrees is equal to 72 over Vx. And so therefore Vx equals, I'm just doing this a different way, 72 over tan 40. So when I do that, 72 divided by 10, 40, make sure I'm in degrees. I get 85. Everybody else get 85, 86. So Vx should be in red there. Vx is 86 feet per second. So right here, I guessed 60. I was off there. I would lose points there, but 86. So I'm going to go flat across at 86 all the way to 4.5 seconds. Okay. So that would get, God, it's terrible. I should do a straight edge. Oh well. And then here, the area, I can quickly find this. I could do it up here. Let's do it this way. That's 86 feet per second, and then multiply that by 4.5 seconds. And that'll give me how far it is. So 80 times, you got 300, yeah, 386, what I got around there. So that means that this ends up at 4.5 seconds at 386. That's 400 right there. It's about 386. I put my straight edge on it and voila. Okay. Now what we had them do, we're out of time here, but what I had them do is they had to go to the board and sketch, number one, without doing any numbers, sketch what it would look like. And it's a type 1 projectile motion. So remember that this then is always going to be flat, always. This is going to look like that, always. This will always look like that at negative G, right? Always negative G. Now the thing is, we know that this always looks like this, but how much of it are we going to get is the question. So I told him that since type 1 projectile motion, which means that there's no positive velocity. So your initial velocity is right there. Then it's going to drop at 9.81. This is English units. No, it's metrics. Okay, it's going to drop at 9.81 meters per second. And I know this guy then is going to be a parabola like that, but it starts off flat. So I already have the general shape of the graph. And that's those things that if I were grading a test now and I came around and I saw this, I would give this person probably a 12 out of 20 because I don't see any work over here, but they knew how to draw, they knew how to sketch the graphs. And then I want you to do the same thing. We made them do the same thing at the board. As far as the duet goes, the duet will always look like this, okay? On all of these, on all projectile motion, the red duet always looks like that. Always positive, okay? Now, but the blue depends on the situation. If it's type 1, like we just did, the example, then blue is right there. If it's type 2A, blue is that one, the perfect bow tie. But if it's type 2B, it can be any of these 4. Okay, and that's where you got to figure out, well, which kind of shape is it? All right. So that was a lot in an hour, in 50 minutes. Hope you enjoyed our trip to Mars. We don't have the luxury of time this year, so I debated on even doing it, and then I thought, how often do we go to Mars? Let's have a little fun. All right, so hopefully you enjoyed that. All right, I'm going to let you guys go, and I'll leave it on. I'll stick around and answer any questions you have at the end. Otherwise, you're free to go. But we don't meet tomorrow. We don't meet Friday, but you will see that. Oh, and you'll see a take-home test video key by 3 o'clock and maybe 3:30 today. Somewhere in there, you'll see it. I have it. I got to film it. Yeah. So I'll see. So Friday at 2 p.m. you can start to take the test. I'll email it to you, and have till 6. You'll have till 6 p.m. on Saturday to get it back to me. I'll also put it on my front porch. I also have another equation sheet packet. I'll put some of those in the front porch if you don't want to do the PDFs. Okay. Now I'm done. So I'll see you guys. See you on Monday, actually, again.
I have a question.
Yeah.
So this test, right? Are we just supposed to study take-home test 4B?
Take-home test 4B will get you 270 points if you did it perfect, right? And then there's 30 points where I can hold back as a surprise. But everything that's on the test we've talked about.
All right.
But that is the best thing to do. Study that.
And do we have to like bring it over to you when we're done with the test?
You can PDF it to me. Or PDF it, don't give me a picture of it because I got to print that out. And pictures are horrible. So you got to PDF it to me, not pictures.
Yeah.
But I'd rather you bring it by, but if you doesn't work, I'll take a PDF.
All right, thank you.
Okay. You got anything, Bennett, or did you fall asleep? Oh, I'm still recording. Uh-oh.